Alright, hello. Welcome to episode 4. I'm going to be talking about the separation of variables technique for solving differential equations. So, essentially, what we mean by separation of variables is it's based on this notion of separability. So, an equation f(t(y) equals g is separable if it can be written as h of t times y prime equals g, right? And we're only considering first order linear right now, right? Remember, first order linear ordinary differential equations. Because what we can do in this case, we can completely separate the variables of y prime and t, then, or actually this is actually h of y, not g. G is a function of t, so we can completely separate t and y. We can separate these variables. Then to solve this differential equation, well, we just need these antiderivatives. So we'll say that h is going to be the antiderivative of, so we're going to say h prime of y is equal to h y prime, and then I'm going to say big G t is equal to g. Big G prime is equal to g, right? So we have these, we wanted to find these antiderivatives, right? And then once we get that, that makes sense. I accidentally went too far back and I can't find the back button. Yeah, so we don't actually want to think about this y prime yet, or yes, we don't want to think about y prime just yet. Jumped ahead of myself, but we want to think gt, right? Big G prime is equal to gt, right? And then so with the chain rule, when we apply the chain rule, then this y prime is going to show up, right? So what we end up doing, well, so we to solve this, well, we just want to take the antiderivative. We just want to take the antiderivative of y prime is equal to antiderivative gt, dt dy. Well, this is just going to give us hy is equal to g, or big G, big hy is equal to big gt plus c. And that's our solution, right? So we can write this solution, some equation in terms of only y, some equation in terms of only t plus c, right? Yeah. So to solve this, we only need to find this h and this g, and then we can, once we do that, then we've essentially solved that. And this is where I talk just briefly about implicit solutions. Implicit solutions. So sometimes it's actually not possible to get an actual solution to h equals g plus c. So in those brief cases, okay, we will have implicit solutions. That's what they're called. Implicit solutions, where if we go back to our rectangle, right, we have, remember, AB, where our solutions exist, and CD, where we have our y. We have our some initial condition, or backwards, and so we have some initial conditions, right? So y of t naught is equal to y naught. That when applied, we can solve this for, c. So c is equal to h y naught minus g t naught, right? this is going to give us some constant, so we can just essentially get an equation that we can solve when we plug those values in, right? And that's kind of the gist of that. This kind of makes more sense when you actually start looking into specific examples and stuff like that, which I'm not going to do, but I might do that later. The next thing that I want to tackle is actually the, I think, Bernoulli equation, and then I think after that I should be ready to actually start talking about physics, and we'll go back to physics.